Okay, so this question 5 is given us what the beta 0 hat is, and it's trying to show what the um, that the r square will be equal to 0. Okay, that's what we're trying to show. So if the regression line passes, if the regression line has a slope of 0, then r square must be equal to 0. Okay, so let's think a little bit about this graphically, what it really means graphically. It means that if I were to plot those data points, if I were to plot the data points, that simply means that the slope of my fitted OLS line is going to be flat. This is going to be my beta 0 hat, and then the slope is going to be beta 1 hat is equal to 0. Okay. You already should know from the formulas that beta 1 hat really captures the covariance, the sample covariance between the x and the y. Okay, and you already know that r square is related with the correlation of these two variables. So if that's 0, you'd expect that r squared to be equal to 0 as well. Okay, that's the sort of intuition. But let's try and do this formula. What's r square? It's explained sum of square over total sum of square. What's explained sum of square? Sum of yi hat minus y bar over sum of yi minus y bar squared. Right? What's next? Well, this is just a definition, so we have to make use of the fact that what is this going to equal to? Right? Because we want to use the fact that beta 1 is equal to beta 1 hat is equal to 0, so there's no beta 1 hats there. Okay? This bottom bit is always as a function of data. This is only dependent on data. Only dependent on data. Now, of course, this thing here is calculated from data. Calculated from data. But we need to calculate the beta 0 hat and the beta 1 hat in order to be able to do that. Okay? We need to do that, otherwise we won't be able to. Okay? So let's do sum of, instead of yi, we can use beta 0 hat plus beta 1 hat times x 0, right? xi minus y bar, all of this squared over sum of yi minus y bar squared. Now, of course, if this expression here, can this expression be equal to 0? This denominator, can it be equal to 0? No, unless, of course, all the y's are the same data points, right? If the y's have any little bit of variance, of course, this thing here will, of course, be different from 0. So if you want to prove that r squared is question mark equal to 0, effectively, you want to prove that this top part here is equal to 0. Okay? But if that top part is equal to 0, and because you have these squares, you really have to prove that every single one of these elements should also be equal to 0. There is no other way of doing it. Okay? Now, let me try and do it slightly with using a couple of the mechanical properties. Well, I know that beta 1 hat is equal to 0. So really what I have is sum of beta 0 hat minus y bar squared over, let's just call it total sum of squares, so I don't have to rewrite the bottom part bit. Now, let me use another mechanical property. What do you know about y bar and y hat bar? They are the same. Okay? What do you know about yi in this yi hat in this particular situation? Because beta 1 hat is 0, yi hat is simply going to be equal to beta 0 hat. If you look at this graph, what's the y hat? It's always the same. It's just equal to beta 0 hat. Whatever value of x I give you, you get the same predicted y. If yi hat is always equal to beta 0, what is y hat bar equal to? It's also equal to beta 0 hat. It's the same number, right? Which means that y bar, because of this mechanical property here, because all predicted y's are equal to beta 0, then their average predicted values will also equal to beta 0 hat. But because of this mechanical property here, I could rewrite this as simply y bar minus y bar squared over total sum squared equal to 0. So here you have it. You have an intuitive way of kind of seeing this with this graphical approach, but you also have a slightly more formal way of kind of doing this with this approach here. Okay. So there's possibly multiple ways of thinking about this, but that's one way of approaching this. Okay. Yeah.
What does the y hat bar? What is it? What's the significance of it? Like, what does that mean? It's the expectation of the
y hat bar is the average predicted value of y. That's all that it is. It simply sums up all the yi hats and divides them by the sample size. Okay? And it's one of the mechanical properties. Yeah.
Can you explain again why y hat bar equals beta 0 hat?
Yeah. So the question is, can you explain again why this bit here holds, right? Well, it's very simple. Do you understand that yi hat is equal to beta 0 hat? For all i's.
Yes.
Of course, because beta 1 is equal to 0, right? Okay, so let's do this. What is y hat bar is going to be equal sum of all the yi hats divided by n. Agree? But what's going to be every single y hat is going to be beta 0, so it's going to be sum of beta 0 hat over n. It's going to be n times beta 0 hat over n, and n cancels, beta 0 hat. What's the average of everything being 5? Well, it's 5, right? It's the same thing. What's the average of a bunch of n numbers that are all equal to beta 0 hat? Well, it's certainly beta 0 hat, okay? That's the statement that I'm trying to make over there. Any more questions on this? Okay, great. I'll stop this here.